this part of section 5.3, we're going to look at some properties of the definite integral and give some real quick explanations of how these work the way they do. So on this first one here, you can see that the property says if we take the integral from b to a of the function f of x dx, and the distinctive thing here is that those limits are opposite what we've seen so far. This is from b to a. Normally it says from a to b. So if you take the integral from b to a, it's going to be the negative of what the integral would have been if you had gone from a to b with the limits that way. So if you switch the order of your limits, the integral becomes multiplied by a negative. Okay, so going from b to a rather than from a to b, you need to throw this negative out front. And the reasoning for that is that changing the order of our limits changes the delta x term in our Riemann sum. So this changes our delta x in the Riemann sum, k equals 1 to n, f of c, k, delta x. Because the normal way that we would find that delta x term would be to take b minus a over n, and we're assuming that b is the larger limit and a is the smaller limit, or b is the upper and a is the lower limit, to use the proper terminology there. And so when we switch those around, okay, and we do delta x equals a minus b over n, that would be the same thing as b minus a over n if you put a negative sign out there, like this. Negative b minus a over n. If you distribute the negative back through, you'll see that it's the same expression there. So that negative kind of propagates its way throughout the Riemann sum, and then we end up with this negative out front of our integral. Okay, so that's our first property, and you'll see this like an example here real quick. If you took the integral from, let's say 4 to 1 of x, just something nice like x squared dx, that would be negative of the integral from 1 to 4 of x squared dx. Okay, so that's how this type of property works. For the next one, number 2, the property says that if we are integrating f of x dx from a to a, the result will always be 0. And that's kind of an interesting thing to look at there. Okay, if you consider x and f of x, if you consider that the definite integral is representing the area underneath the curve, okay, there's some generic f of x there. You're saying, okay, I'm going to take the integral under this curve, and it's going to be the same as the area under the curve, and I'm going to start at a, and then I'm going to finish at my upper limit, which is also a. So I'm going to start here and end here in that exact same place. So your limits are right on top of each other. So it ends up not really going anywhere, and there is no area underneath the curve where that little vertical line is, right? There's no area being encapsulated. So yeah, that's why this is working out the way that it does. There's no area from x equals a to x equals a because it's in the same spot. And so our integral is going to be 0. No matter what constant a is, that'll work for any value. Okay. Now, the next one here, the integral from a to b. Okay, so we got 2 different limits again. The integral from a to b of a constant c times f of x dx. Okay, c is any constant. All right, we're seeing here that the property says you can pull that constant c out of the integral and multiply it instead of multiplying it inside the integral. And the reasoning for this is because of our constant multiple from the sum properties, constant multiple property for sums. Okay, this was in our, what was it? The algebra of sums, I think is what we called it in section 5.1. So that property looked like this. If you were taking a summation of a constant times some terms, like this type of thing, you could pull the constant out of the summation, right? C times the summation of the a sub k's. And since we know now that integrals are based upon summations, these integral properties are going to match up with a lot of our summation properties. So it works the same way for definite integrals as it did for finite sums. All right. And you'll see that here in number 4 as well. If you're taking an integral of two functions that are either added together or subtracted from each other, a sum or difference there, it turns out you can split this into two integrals. So these were from our sum and difference properties. Okay, if you recall those. Sum and difference properties for summations. Okay, which said if you had a single summation that had two different sets of terms within it, like the a sub k plus b sub k's, this one's a sum property in this case, since I'm adding those two things together. It said you could split that up into two separate summations and then add those separate sums together. Okay, and since a summation, we're taking that now to correspond to our integrals. We're taking the limit as n goes to infinity of these sums here. Each one of those is going to match up with its own little integral. So we're going to kind of like your a sub k is in place of f of x and your b sub k's are in place of g of x. So that's what we're looking at here. And it's going to work the same way with differences. If there's subtraction here, you would just subtract those separated sums. And then in terms of integrals, you would just subtract the integrals. Whatever the original operation was, that's what the new operation is. Okay. Number 5 here. This says if we're taking the integral from a to b of f of x dx, and we're adding the integral from b to c of f of x dx, that's going to equal overall the integral from a to c of f of x dx. Now watch the limits carefully on this one, but we can see this one, I think, pretty nicely in a picture. Let's set up a real nice little generic function for ourselves. Whatever you like. Yours might look a little different. That's okay. All right, let's call this point A, this point B, this point C. And so this first integral here, going from a to b of f of x dx, we know that that's representing the area underneath our curve from A to B. So that would be this area right here in orange. Okay, so that's that guy. And then the integral from B to C of f of x dx would be starting from B and going to C. That would be this area right here underneath the curve. And when we add those two areas together, you can see that we're getting this whole thing from A to C underneath the curve. We're getting all of that area covered. So overall, we get the integral from A to C of f of x dx. All right. Now, property number 6, the integral of a constant function. This says if you're integrating the constant function c from a to b, it's just going to be c times b minus a. And why that is, we can see again from a picture. Okay, a constant function c, like y equals c or f of x equals c, that is just a horizontal line. Okay, so this is the value c. So this horizontal line is f of x equals c. And if we're going to integrate that from a to b, that's going to be representing the area beneath our curve, so between the curve and the x-axis here. Okay, we can see that that resulting area is a rectangle, and the area of that rectangle is going to have, it's going to be length times width or width times height, however you like to think about it. But the height of this rectangle is just c units. And then the width of the rectangle is b minus a units. Right, from side to side there. So c times b minus a would give you the area of that rectangle. And so that's why we end up with that formula for the integral of a constant function. They're representing the same thing. And so then the second part here just expands upon that and says that, okay, now your f of x doesn't have to be a constant, but it is bounded between two constants. Okay, so little m is some small constant value, and big M is some maximum constant value. All right. So we would say, let's see, here's little m and here's big M, and f of x has to be between those two values. It's greater than or equal to little m, but it's less than or equal to big M. Okay, so f of x, maybe it starts somewhere in the middle here and then maybe equals uppercase M at some point. Maybe it goes down and equals little m at some point. It doesn't have to, but it's either between those two values or it could equal either one. All right, so this is f of x. Yours may look a little different. But all this is doing is saying that, okay, if your function is bounded between those two constants on the interval from a to b, then your integral value is just going to be somewhere in between the area of the two rectangles formed by those constants. Okay, so if we look at little m times b minus a, that's just the area that's being formed between little m and the x-axis here. Okay, so that would be this part right here. There's little m times b minus a. And then big M times b minus a would be up here, creating another rectangle. Okay, and it kind of overlaps the other one that we saw. Okay, so the green is stuff that is part of big M times b minus a. And then our actual integral is going to be the area between the curve f of x and the x-axis. So that would be this portion right here, which is not a rectangle, but that's okay. We can still estimate or give bounds to how much area that will be by looking at the size of those two rectangles that are bounding it. That area is definitely greater than or equal to the orange rectangle, and that area is less than or equal to the larger green rectangle area. So that's what we're looking at there. Okay, now property 7 here also follows a similar idea. It's just got two functions now. If your function f of x is greater than or equal to g of x on the interval from a to b, let's sketch that. Okay, so let's put in two different functions here. Let's say this guy will be f of x. I'll make that orange. And g of x will be blue. And f of x is always greater than or equal to g of x on our interval. Okay, outside the interval, we don't really care what they're doing, but okay, let's make at least one point where they're equal there. Okay, so there's a g of x, that'll work. And let's identify a little interval here from a to b. Okay, so then this says that the integral from a to b of f of x dx, that would be this orange area that I'm shading in. That is greater than or equal to the integral from a to b of g of x dx, which is going to be the area between g of x and the x-axis, which I'll shade in blue here. Okay, and we can see that, yeah, the integral or area for f of x is greater than or equal to the integral or area for g of x. So yeah, that'll just hold because of the way these integrals relate to area beneath a curve. It's a nice property to have. And then the little extra detail here, this is just a special case of the property that we just looked at here, special case where we let the function g of x just equals 0. So if this is flat on the x-axis, so if f of x is greater than or equal to 0, the function values are never negative on the interval from a to b, then the resulting integral is also not going to be negative. Its value is going to be greater than or equal to 0. And you can think of that in relation to the idea of net area. Things above the x-axis have positive net area. Anything below the x-axis would have negative net area, but this right here is saying that we don't go below the x-axis in this case. All right, so there's property 7. Now there's one little extra additional property or theorem. The book does not include this one with the previous 7 properties, but it's kind of along similar lines. If f is continuous on the interval from a to b, or if it has a finite number of jump discontinuities on that interval, then the integral from a to b of f of x dx exists. So the function is going to be integrable, which is a nice thing to know, that we can actually take the integral. Okay, so continuous functions, that is totally cool. That's what we've been graphing this entire time. All of these little f of x's, g of x, these are all continuous functions. So that's pretty much the normal case, okay, that we've been looking at. So continuous. Then the more interesting one, and this does happen less often, definitely, is if we have a finite number of jump discontinuities on our interval. And so I've drawn us a little graph here earlier to make a nice jump discontinuous function. I'm gonna grab this, if it'll let me, bring it on in. So you can sketch a function with a little jump discontinuity in there. All right, so notice how this function on the interval from A to B, it has a jump discontinuity at one of the endpoints, at A even, and then there's one in the middle of the interval as well. But the part that's shaded in underneath the function, that is the area between the function curve and the x-axis, and that is not actually being affected by our jump discontinuities. This part right here where the jump discontinuity is, that's like along a vertical line, so that wouldn't have had any area associated with it anyway. Okay, same thing right at the end point here. That jump discontinuity lines up along a vertical line. There would have been no area there either. So the jump discontinuities don't affect the area under f of x. Okay, now note that this is only for jump discontinuities. If you have an infinite discontinuity, like this type of thing, if you've got like a vertical asymptote in there going from A to B and your function does something like this, that's going to be a bit of a problem. All right, because if you're trying to find the area between that curve and the x-axis, well, you'd probably start shading this in, but then as you go up, the function values just keep shooting up and adding extra little bits of area and extra little bits. And so we don't really know what's going to happen to that. And actually, this is something that you're going to handle in Calc 2. Looking at what happens there. So little teaser for the class after this. But that's not something we're going to handle in this class. We just know that if there's a finite number of jump discontinuities, then the function is still integrable. All right, so there are your properties of the definite integral for now.